Hey everybody, welcome to 10.4. Today we're going to be talking about area of regular polygons. And I just put on here just a reminder what a regular polygon is. Remember that it is a polygon or a shape with all congruent sides. That's what the word regular means. So this section here we're going to be focusing on shapes that have all equal sides. That's going to be really important for our formula. Okay? So let's go ahead and just talk about our regular polygons and some unique characteristics that will be helpful today to develop our area formula. So the first thing I did here was I drew a circle, and then within that circle I drew a hexagon, and we're going to assume that in this case this hexagon is a regular hexagon, so every side is the same. Okay. What we can tell from this shape is that they're going to share the same center. Okay, maybe I call it K for the center, and I can draw a radius of this circle in this picture, and this will also be the radius of the polygon. So remember, a radius starts at the center and it goes to the edge of a circle. So I'm going to start at the center here and draw a radius in. Okay, and I could do that to any corner, and that would be a radius of both the circle and the polygon. Okay, so they share the same radius. That's kind of nice. I also have this new vocab word down here. It's called the apothem. Make sure you write that down. So the apothem is a segment that goes from the center of the shape and then goes perpendicular to the side of that regular polygon. So let me get a red here. Okay, so from the center, I'm going to draw a segment that creates a nice 90-degree angle to the side of the regular polygon. Okay, so that's called the apothem, and this is going to be very helpful because this is the height of a triangle. Okay, and then the only other thing that's going to be really helpful in this section is going to be our central angles. So remember, a central angle is an angle starting at the center that goes out to the edges of a circle. It's made up of two radii, or two different radius segments. So all I have to do to figure out what this measure is take 360 divided by the number of sides. That's what the n is. So in this particular shape, my central angle measure for K would be 360 divided by 6, because this is a hexagon, and that gets us 60 degrees. So this angle right here is 60 degrees. And just as a little reminder, remember, central angles are the same as the arcs, so this arc measure would also be 60 degrees. Okay? So let's use this concept and practice identifying some things within our regular polygons. So here I have a circle, and then I have a rectangle drawn in, and we want to identify these different things and then also find the central angle measure. So starting off with the center, hopefully that's really easy. That's going to be point A. Okay, so that's the center. And then we can go ahead and find a radius. So the radius here, we have two different options. We can go from A to B, or we can go from A to D. Okay, so segment AB, I hope you can see that, and then segment AD. Those would be two options. Okay, and then we can go ahead and find the apothem. So the apothem is from the center and goes perpendicular to the side. So I'll scribble that in green. So the apothem is going to be segment AC. And then our central angle is going to be, let me get a highlighter here, from the center out. So from D to A to B. So notice I highlighted that whole thing, that whole angle right here, all the way around. So I'm going to say angle DAB, or you can call it angle BAD, doesn't matter. And if I want to find the measure of that angle, remember that we take 360 divided by the number of sides. Well, I've got a rectangle here, that's 4 sides. So this angle measure that I just marked would be a 90-degree measure, and that's it. Okay, so hopefully those couple things are really easy to identify. They're going to be very helpful in this next couple examples. Before we go ahead and actually introduce the formula for regular polygons, I just want to show where we're getting the formula. So we're going to go ahead and start off with this example of finding the area of a regular hexagon. And just in case you've forgotten, a regular hexagon has 6 sides. So I'm going to go ahead and draw that in. Just do the best you can to draw in this shape in your notes. And they tell you that the apothem is 18 inches. So I'm going to draw the apothem in. Remember, apothem starts at the center and then goes perpendicular to the side. So I've got a nice right angle here. and that was 18 inches. And then they tell us that every side length here is 15. So I'm going to just label this bottom side as 15 inches. Well, looking at this, it's kind of hard to tell how we could find the area, and we don't have a formula yet. So the easiest way to do this is to break this shape up into isosceles triangles. And triangles, we know how to find the area of. So what I'm going to do is I'm going to add a radius into this picture. So a radius here and a radius here. And by doing that, I've now just created this nice isosceles triangle. Okay, and it is isosceles because the radius is the same on each side. So here's our isosceles triangle. And now all I have to do is find the area of this one shape and then multiply it by the number of triangles I could fit in this picture. So let's find the area of that triangle first. So the area of the triangle is 1/2 base times height. We should know that at this point. So I'm going to have the area of the triangle is equal to 1/2. The base is 15. And the height, or our apothem, is 18. So I can go ahead and multiply all of that together, and I get half of 18, that's 9. So 9 times 15, that's going to get us 135. So the area of the one triangle is 135 inches squared. The problem is that that's just for this one triangle. Well, how many triangles could I fit into this picture? Well, to figure that out, I could go ahead, I'm going to do it in green. I'm going to add a couple different radii into my picture. So there's another triangle, another one. Okay, all I did is just draw a radius to each corner. And by doing that, I've created a total of 6 triangles. So 1, 2, 3, 4, 5, and then the 6th one here in the middle. So if I know I have 6 total triangles, I just found the area of one of them. So to find the whole area of the hexagon, I'm going to take the area of the one triangle times the number of triangles. That was 6. And when I do that, I'm going to get 810. So the area of my regular hexagon is 810, and that's going to be in inches squared. Right? Now, rather than finding a triangle and then multiplying it by the number of triangles that there are, instead of doing this every time, what they did is they used this concept and the fact that we know the apothem, okay, to help us come up with this nice formula. It's pretty short, and it's right here. Okay, so you want to make sure you write this down. So this is A equals 1/2 little a times P. And little a is the apothem. Remember, we just talked about what that is, from the center to the side of a polygon. And then P is standing for our perimeter. So remember, to find perimeter, we just add up all the sides. So this is taking care of having to calculate how many triangles there are by just using perimeter instead. So we're going to use this formula, and we're going to find the area of this regular octagon. Now just keep in mind that they won't always give you everything you need right away. Okay, so in this case, they give us the A, that's the apothem. So right now we have 1/2 times 8, but the problem is that we don't know what P is. Okay, so we don't have the perimeter yet. So we're going to have to use a little bit of extra information to help us find that perimeter. So to do that, we're going to go ahead and add in some radii to our picture, so that way we have an isosceles triangle again. Okay. So the isosceles triangle is going to be very helpful. Now, unfortunately, we don't have any other information. So what we're going to have to do is use what we used in the last couple pages, is that central angle. Okay, to find the central angle, remember we take 360 divided by the number of sides. Well, this is an octagon, so we're going to divide that by 8, and that's going to get us 45 degrees. So this whole angle is 45 degrees. Okay, so we could do one of two things. We can go ahead and find the other missing angle measures, or instead, because we know this is a right triangle here, I could go ahead and divide that 45 degrees by 2. And when I do that, I get 22.5. And so now what I have here is this angle in red. Okay, I'm going to draw it out to the side. That's 22.5 degrees. And that allows me to use this right triangle, okay, to solve for this missing side. And I'm going to just label it as X. So I've got a right triangle, I've got an angle, and I've got a side. So this is going to allow me to use some SOHCAHTOA. And yes, you might have to use SOHCAHTOA. Okay, You're going to have to see it a lot. Hopefully at this point we're comfortable with it. So I'm going to go ahead and set this up. So from this angle, I've got the opposite and the adjacent. So that's going to be tangent. So I'm going to say the tangent of the angle, 22.5, is equal to the opposite, that's what I'm looking for, over the adjacent, that's the 8. What this is going to allow us to do is find part of the outside perimeter, and then we can add up all the sides. So to solve this, I'm going to multiply both sides by 8. So that will cancel. And then I just have to type this into my calculator. So 8 times the tangent of 22.5, that's going to get me a side length of 3.3. So right here in that X spot, I'm going to put a 3.3. Now be very careful because that's not the whole side length. That's only half the side length. So if this is 3.3, so is this, because it's an isosceles triangle, got broken up. So now we know the whole side length here is 6.6. And this is going to allow us to go ahead and find that perimeter that we were missing. So to find the perimeter, we just take 6.6, remember that's one side length, times the number of sides that we have, which are, we have 8 sides. So now I can just go ahead and type in 6.6 times 8, and that's going to get me a perimeter of 52.8. And now I can go back to my formula, and I can plug that in, so 52.8. And now I have everything I need for my area, so I just have to type this in the calculator. So half of 8 is 4. 4 times 52.8, that's 211.2, and this is in inches, so inches squared. So then there is my final answer. So notice I had to do some extra work to find that perimeter, but I didn't have to worry about any of the other triangles. I just used what I knew. So I had the apothem, I plugged that in, and then I used SOHCAHTOA and right triangles to find my missing side length, and then all I had to do was find the perimeter. Okay, so there's a couple things that you're going to have to potentially use in this section. You might have to use SOHCAHTOA. That's going to be really important. You might also have to use Pythagorean theorem, potentially. Okay, you're going to have to know how to find a central angle, so that's going to be important. So if you don't know how to do that, remember that's 360 divided by n. Okay, and then you're going to have to know your vocab. So you're going to have to know what perimeter is. You're going to have to know what an apothem is. That's the newest vocab word. Okay, radii, you're going to have to know how to draw those into the circles. All of those things are going to be very helpful in finding these shapes. And you can do this for any regular polygon. So I could do it for a square. I could do it for a dodecagon. I can do it for a heptagon, a nonagon. Any of these shapes you can do them for. So you just need to know that formula. Area equals 1/2 apothem times perimeter. Make sure you have that written down. Make sure you write the examples down, and then we will go over this in class if you have any extra questions. Thanks for listening.